edge designations, CFA level 1, pre-reading, quantitative methods, learning module 4, common probability distributions. We continue onwards as promised from video 1 with more and more distributions. Next one is the normal distribution. Normal distribution should make everybody get a little bit of a warm fuzzy feeling, I hope. It's the one that we deal with the most, very common distribution. And yeah, let's have a look over here at some of its properties. Well, first and foremost, I'm sure everybody's quite familiar with its picture, how it looks. Okay, what do you notice though? We've written something very particular on its top. Fx. Now remember what we said about f. F is continuous. Remember that. Okay, and look at now. Let's write that out for you. It's a continuous distribution. Look over here. The normal distribution is a special continuous distribution. Okay, the mean is normally in the middle with its median and the mode. Remember, the median is the number that comes up the most often. Is the middle number. Apologies. The mode is the number that comes up the most often. If I had to ask you a little question over here, remember all of this over here, which I'm highlighting, scratching in my blue color. What would you call that? That's the area under the graph. And what would you call that? 100%. Okay. Because the normal distribution is split down the middle with the mean left-hand side, right-hand side, we would expect the left-hand side to have 50% of the observations probabilities and the right-hand side to have the other 50%. Yes, of course, that then would sum to 1 or 100%. We've seen all of this before. Okay. And top of page 14, the key property of our graph is that of symmetry. In other words, it's symmetrical about its mean, median, and its mode. And remember, when we read what we're reading over here with the normal distribution, I always encourage you to go back to learning module 2, where we started off talking about things like means, medians, and modes. Okay, I'm not going to spend too much more time over here. Just to tell you, because the graph is symmetrical about its mean, the area under the graph, yes, we know equals to 1. Why does it equal to 1? Because probabilities sum to 100%. This should not, I'm hoping people are starting to see the flow over here. Okay, each side of the graph then represents 50% of the total area. It's perfectly symmetrical. If it's symmetrical, no part of the graph is skewed to either side, not to the left, not to the right. It therefore exhibits zero skewness. What do we know about kurtosis? Kurtosis is a measure, not a rare medical disease, as one student once told me. No, kurtosis is a statistical measure, but normal kurtosis, kurtosis measures the amount of peakedness in the distribution. And if it's a normal distribution, kurtosis is equal to 3. Let me just illustrate that for you. Okay, there is a normal distribution. Okay, the kurtosis in this particular distribution is equal to 3. If it were what we would call there's different kinds of kurtosis. There's leptokurtic. Leptokurtic means it looks like that. It's got what we call a peaked distribution. Okay, it all sits in a very specific area that we call leptokurtosis. Platykurtic is it's much more flat. It will look a little bit like that as a distribution. Our one is called, okay, it's the normal or mesokurtic, where it has a kurtosis measure of 3, and all of these are the properties then of the normal distribution. As we move into the later sections of the particular notes, which we'll see particularly in learning module 5, as we move to sampling and estimation, what we notice, okay, is that 90% of all observations fall within 1.645 standard deviations of the mean. And you're saying to me, that sounds like Greek. Let's show you what that means. Here is my normal distribution. There is my mean at 0. 0, no standard deviations. It's exactly in the middle. It doesn't move not left, not right. If we move 1.645 standard deviations, so we go to there, both left and right. Now, if at this particular point in time, This would be 1.645 standard deviations. What does it mean, standard deviations? Deviations from the mean. That side is minus 1.645. Why is it minus? Because it's on the left-hand side of 0. But if we move 1.645 standard deviations away from my mean, from my normal, because remember, guys, go back to learning module 2. What is the standard deviation? Standard deviation is derived from the word variance. Variance means it varies. Varies from what? Varies from your mean, or is dispersed away from the mean. If we go 1.645, and it's a standard measure called a standard deviation from the mean, what does that tell me? This tells me that how much of my probabilities have I got enclosed in that particular area. Tells me 90%. And the further you move left and right, and obviously this we can see this visually, the more you move left and right, guys, the greater the amount of observations that you are going to include in the total probability. Okay, I'm not going to spend much more time with it. We will see those when we get to the next section as well. Example of mean and variance. Okay, the mean and variance, just by way of example, guys, of a price to earnings ratio of all companies in a given industry are 30 and 16 respectively. That's the mean and the variance. And if I had to say to you, if the PEs are normally distributed, now guys, you always hope and pray that in a distribution you're dealing with a normal distribution. Where would 50% of the PEs fall? What do we know? And again, guys, this goes back to here. Approximately 50% of all observations fall within 0.67 standard deviations of my mean. Okay, and the example will be nice and simple. All I would need to do over here, I would take my 30, which is my mean or my average, less 0.67. 0.67 comes from there because 50% fall within there. Okay, is everybody comfortable with that? Why do I use 4? Where's that 4 from? Remember, 16 is my variance. How do you go from variance to standard deviation? You root it. So the variance, okay, was equal to 16. Standard deviation is equal to 16 rooted is equal to 4. And all I say then, well, 30 is my mean or my average, less 0.67, which is where 50% of the observations will fall of the standard deviation, is 27.32. On which side? The left side. And 30 plus 0.67 times 4, 32.68 on the right side. Is everybody comfortable? Because remember, guys, if in this particular example I wanted to draw you a normal distribution, it would look like that. There is my mean. What's my mean over here? The question told me 30. 50% of the observations fall within minus 0.67 standard deviations to the left and plus 0.67 standard deviations then to the right. And that would include how many of my observations? Not exactly so well drawn over there, but hey, 50% observations. What number would 0.67 to the left and plus 0.67 to the right be? We've shown you those calcs over there. On the left hand side, I'm minusing, so that is equal to 27.32. That's that number there. And on the right hand side, it's 32.6. So if I'm working within that particular range, how much of the observations have I got? 50%. Go through this example again, guys. It's a good one, and it'll show you exactly what you need to know in terms of what we're looking at in this particular case. We move on. Okay. Top of page 15, have a look at the difference between a multivariate. What's multivariate? Sounds fancy. It's not so. Multi is many variants, and uni is one. That's all. Simple, simple. Okay. We talk about two kinds of distributions. Univariate, the distribution has only got one random variable, and a multivariate distribution, it's got two or more random variables. Now hopefully all these words are familiar to you. Okay, two or more random variables. Random means we don't know the outcome before it started. Discrete, we know we can count them, we can list them. Okay, and continuous, we know its properties over there. Okay, we move on. We're talking now a little, and we're going to see this throughout the quant section, okay, is the role of correlation in a multivariate. Now remember, why are we only ever going to see correlation in a multivariate distribution? Because what is correlation? Correlation says I've got two different items. Are they linked to each other? In other words, is there a correlation? Is there something that makes them work together? Okay, and that's obviously what we're working on here. It's called a multivariate distribution. Is everybody comfortable with that? Okay, multivariate, multi means two or more random variables, and now I want to know these two or more random variables, is there a correlation between them? Are they linked somewhat? By way of example, let's say I gave you two random variables. Number one random variable is the amount of hours that my students study for. Number two are the grades that they obtain. Those will be two random variables. Number one, hours studied. Number two is the grades obtained. Okay, what I want to find out between these two variables, the amount of times that they study, hours, and the grades that they obtain, is there a correlation? Is there a link? Because I want to go back to the students and say, listen, the longer you study for, the greater your grades are likely to be. But can you see, we can only talk about correlation when we talk about a multivariate distribution, because if it was a univariate distribution, only one item, well then there wouldn't be any correlation, because nothing can correlate with each other, with itself. But of course, if it does, of course, that would be what? If something correlated perfectly with itself, well, it would be only one item. Okay, let's have a look over here. We go over our page over here, okay, and I don't want to speak too much more about this over here, guys, because we will see this when we get to further on into the quant section, specifically dealing with things like correlations, covariances, and things like that. But just something to take out from you over here, guys, is that you've got two kinds of distributions: univariate, okay, which is uni meaning one, okay. If I just take you back over here, okay, you've got your univariate there and your multivariate there. And remember, when we talk about things like correlation and how things are linked, has to be talking then about the multivariate distribution. Okay, we continue onwards over here, and we're going to calculate the probability that a normally distributed random variable, guys, I'm hoping these words are starting to make sense to you, lies inside a given interval. The key word we talk about over here is a point estimate. Now, a point estimate, remember, guys, look at the words over here. I'm working with samples. Because I'm dealing with a sample, I don't know 100% that it's right or wrong, do I? I don't know with 100% certainty that the value is what it is. Because remember, if I worked with a whole population, then yes, of course, I would know exactly the value that I'm dealing with, because it's the whole population. I'm not working with a sample, and I don't have to try and estimate my points, which are called point estimates. What am I trying to estimate, guys? Most of the time I'm trying to estimate the mean or the average. Okay, could be variances, things like that. But remember, most of the time I'm trying to estimate what point? The point being the mean for the most part. That's what we're going to be working with. Why do I need to estimate? Because I'm working with what? Samples, not populations. Okay. Now remember, I'm working with a sample. Everybody comfortable? So I work with my sample. If I had to say to you guys, listen, hold on a second, how many soccer balls are out there in the market? Oh, there's 1 million. What would we call the 1 million soccer balls? The population. I wanted to, and someone said to me, you know, this particular soccer ball that's been brought out by a particular company, it gets flat very quickly, loses its air very quickly. So I say, oh really? Let's test that. So what would be the best way to test that if I had tons of money, tons of time, and I could get you every single soccer ball? Well, what I would do is I would buy every single soccer ball in the market, okay, which is what we're going to call the population. Everybody comfortable with that? I'd buy the entire population of soccer balls and I would test them. Of course, guys, that's not practical. So what I do, I then go and select myself a sample of soccer balls, okay, and let's call the sample 100 soccer balls, and I test those. Obviously, remember, guys, when you're selecting a sample, just make sure that your sample is representative of the population. But now I'm testing 100 soccer balls, and I'm trying to infer from that about the whole population. Well, I can't do that 100% accurately, can I? We now come to the next concept called a confidence interval. A confidence interval says, well, how confident do you want to be? Okay. And because I want to be a certain amount confident, let's say, for example, 90% confident, this is where some of the more difficult quants starts to kick in. Guys, I want to be a certain amount confident. What do I do? Let's say 90% confident. What do? I use my tables. There's what we call a normal distribution table. I go to the table, and the table says to me, oh, you're working with a sample, and oh, you want to be 90% confident. Let me give you a factor for that. Your factor is 1.645. Okay. Is everyone comfortable with that? So remember again, point estimate. Why am I working with an estimate of my point, an estimate of my mean, and not the actual mean? Because I'm working with what? I'm working with a sample, not a population. Confidence interval says how confident you want to be that you are correct. Well, I want to be 90% sure that I'm correct. I go to my normal distribution table, guys. It's called a Z table. I go to the Z table, and I get a factor. Some people call it a Z score, Z factor. Okay, confidence factor. It's got many different names. 1.645. Let us do an example over here. Then on page 17. The grades of a sample. Straight away, you see a sample of 36 university students have got a normal distribution. The mean is 60%. And standard deviation is 10. Now, big question, guys. If I've already got the mean being 60%, I know that it's 60%. Why do I have to do any more work? I know it's 60%. I drew a sample of 36 students, and I got to a mean, an average of their marks of 60. Why am I not happy with that? Well, remember, there weren't 36 students in the class. There were 3,600. That's the whole population. Okay, it's a big varsity. Okay. So if I got the marks of what, guys? All 3,600, then I'm quite confident. I don't. I've got the marks of a sample. I want to work within, my standard deviation is 10%, and I want to work within 90% confidence. So straight away, guys, when you get a confidence level, I go to my table, I read off my table. My table for 90% gives me, you can learn these off by heart, which is not a bad idea to learn a couple for 90 and 95%. You can even learn 99%. You can learn those numbers, or you can, in an exam, they will give you the table. I go look on my table, and I get a number then of 1.645. What does 1.645 mean? Look, now I'm ready to calculate my point estimate. My point estimate is as follows, guys. My point estimate starts off with, what did I get? The actual number I got was 60%. Is everybody comfortable? I now go to get my point estimate, my range, plus or minus. So I open my brackets, I put my factor in of 1.645, and I multiply that then by the standard deviation given. Now we can say, let's go again, 60% plus or minus, what's 1.645 times 10%? 16.45%. Now I can conclude, what's my range, guys? My range is going to be 60% plus 16.45, which is equal to 76.45, or 60% minus 16.45, which then is equal to 43.55. That is my range. Is everybody comfortable with that? My lower limit of the range, okay, is 43.55. Okay, and my upper limit is 76.45. In other words, why don't I just say 60%, guys? Because that's what I calculated via my sample. No, I can't say 60%, because yes, that's what I got via my sample, but what that particular number, okay, is based upon a sample, not based upon a whole population. Therefore, I've got to use a factor. I want to be 90% confident, okay, and I use that particular factor. Okay, if I wanted to be more confident, look over here. Let's say, for example, I wanted to be 95% confident that my sample was correct. Again, same story, guys. I go to my table. What table? I go to the table which is called the Z table, which is the table for the normal distribution. And I say for 95%, what's my factor? And what do you notice? The factor goes up from 1.645 when I want to be 90% confident, goes to 1.96. Because now what happens? Now I want to be what, guys? More confident. I want to be 95% confidence. What do you think that's going to do to my range of numbers? Well, now my original range of numbers was from 43.55 up to 76. Look at my range now. 40 to 79. What's happened to my range? My range has gotten wider. Why has it gotten wider? It's gotten wider because I want to be more confident. If I want to be more confident that I'm correct, well, I've got to work within a much wider range. You want me to be sure? I've got to give a bit of a wider range then. I say I'm 95% sure that it'll be within this big range over here. If you want me to be even more sure, 99% sure, well, my range is going to just get wider and wider. Everybody comfortable with it? Okay. We go on to page 18. We're going to talk a little bit here, a little bit more about these standardized random variables. Okay, let's talk. These are called Z scores. Okay, remember the Z scores that we spoke about over there. What was my Z score? 1.645. And what did we say? Guys, just going back a little bit. When we said 1.645 or 1.96, 1.645 was 90%. 1.96 was 95%. So we're working now when we work with to calculate the Z, and remember that was my Z score. Now I'm going to show you how to calculate the Z. Is everybody comfortable? Okay. Now, so the Z, what does the Z represent? Then a percentage. What did we have before? We had a percent, and then we went to look on the table for the Z score. This way, okay, when we're standardizing a random variable, what I do, I first calculated the Z score. How do I calculate it? My actual observation, guys, always your actual observation is equal to an X, less the population mean, which is the mu, over the population standard deviation. There we go. Is everybody comfortable? Okay. Once I've done this particular calculation, what will this give me? This now will give me my Z. Now I take my Z and I go to the table and I work on the table, okay, and I calculate then from the table, okay, a percent. You can see I'm just working the other way around now. Okay. And once I've got my Z, I can get a percent then from the table. Is everybody comfortable with that? Let's just have a quick look over here. The population's got a mean of 10, standard deviation of 5, and it said standardize the number 15. So what would we say, guys? Okay. What do we know? Look, let's just take you back to my formula. Actual observation less the mean. So actual observation 15 less the mean of 10 over standard deviation of 5. Is everybody comfortable? Equals a standardized number of 1. Once I've got my 1, what would I do, guys? I'd go and look on the table. And what would the table give me? It will give me a percent. What's the percent? And that's a probability. We know that. Okay, everyone comfortable? Okay. And let us, I'm just going to show you this over here, guys. Let's look over here. Okay. Once I've got my numbers, let's do this example. Actually, it's a lovely one. Okay. Okay. Let's go here. Okay. And when we look over here, I'm just going to show you this. I won't go into too much detail. Okay. We look at the particular numbers and we can see once I've got my Z factors, I can then go and look. There's my factors. I can then go and look at my various numbers. Okay. And I can calculate probabilities. Because remember, here's my normal distribution. Okay. On both sides. Once I've got my Z, I can go look at the Z table, but can everyone see how the two of them work together? We can either be working with Z factors, which we've shown you now how to calculate, Okay, and that'll give me a percentage or some kind of a probability, or I can work with the probability and then go and get those then from the table. Okay, let's have a look over here on page 20, and let's have a look. Okay, I want to do a nice example for you here. A lot of it's been a bit theoretical. Let's go and do some numbers. The heights of the people in a city with a normal distribution, mean 170. Guys, straight away, what would you tell me that is? It's denoted by my mu. Standard deviation 10. What denotes that, guys? There we go. Look what the question's asking you here. This is important. Calculate the probability that if I choose a random person, okay, from the particular population, that they've got a height of, I'll work with the first one, less than 180 centimeters. Is everybody comfortable that that's equal then to my x? Let's standardize that. Let's standardize it. Standardizing is what I do when I do my z. So what I do, I say what's x? It's going to be, remember guys, x minus mu over standard deviation. What's my x? 180. What's my mu? It's from there. Minus 170. What's my standard deviation? 10. Okay. Equal to, well, that's a nice easy sum. That's equal to 1. My z, there is 1. Now we go and look on the table. I go to my z table. I haven't shown you one over here, guys. We will do it more when we do sampling and estimation. Okay. And if you are looking, guys, at your notes, it's going to be learning module 7. It's over there as well. Do take a look. We look at 1 on the z table. What do I get? I get 0.84. Of course you get 0 point something. Why do you get 0 point something all the time, guys? Because it is a normal distribution and it is a probability. When I'm working with probabilities, all individual probabilities are, I'm boring you now, less than 1. That's why, of course, it's 0.8413. What could you tell me? So my answer is 0. So I do my z score based on my x. I get to the answer of z being 1. I look on my table. My table says it's 0.8413. Okay, and there is my answer. Now you can just see it on the table. Look on the table. Okay, there's my z as expressed. How much of it sits under the table? 0.8413. So those that have got, now we can see, those that would have a height that's less than that, and I've got my number over there, 84.13%. And you can do a couple of those. I'm not going to do each and every one with you. Do practice those. But always remember, guys, we've got two ways of working with z's. Way number one is I could be given, guys, a confidence level. Let's say I get a confidence level of 90%. Then I go to my chart and I get an answer of 1.645. Number two is I could be given, asked to calculate the z score. And in my example, let's say my z score is 1. I then go to the table and I get an answer of 0.84, which I think I just showed you. And that's the probability there. So we can work with them, guys, in two possible ways. Top of page 22, believe it or not, we continue with those. And there you go. Okay, and I'm not going to do each and every single one with you. Okay. Top of page 23, we come to a different type of a distribution, which is called the student's T distribution. Student's T works with a thing called degrees of freedom. Now, why would I ever go and use the student's T as opposed to the Z? Now, remember, guys, now I'm dealing with a second distribution. Number one was a Z table. This is now going to be called a T table. So you can see very clearly we can deal with two very specific types of tables. A Z table and a T table. Why would I go for T if I've got Z? Look here. When I'm working with a normal distribution, but I'm not given the standard deviation. Guys, if I'm not given the standard deviation, I need to use another distribution, which has also got some nice properties. Not as nice, not as fancy, not as what I would like to use as the normal distribution, and Z, but not so bad. But I have to use it. Why? Because I was not given the standard deviation. That's called the student's T. Student's T always work with degrees of freedom. Degrees of freedom always n minus 1. N is my sample size. Okay, degrees of freedom we see over here. Okay, why is it called degrees of freedom? It sounds like a fancy name. It's the degree to which the t-distribution has got the freedom almost to assume the properties of a normal distribution. Because I don't understand deviation of my population, I cannot, okay, make use of the normal distribution, so I've got to go for another distribution. But I want my new distribution to be almost like, to have the freedom to be like the normal distribution. I use these things called degrees of freedom. Everybody comfortable? Okay, here we go. The t-distribution has got the following properties. It's symmetrical around its mean. The mean is 0. It's defined only by a single parameter, which is the degrees of freedom. It's got more areas around its tail. The tails are a little bit thicker. Okay. Then a Z distribution, we call that fatty tails. If you had to look over here, guys, there would be your normal distribution. Okay, a T's got slightly fatter tails. They extend just a little bit longer than a normal distribution. Okay, as we increase the degrees of freedom, a T looks a bit like a Z. So when you get when it gets quite wide, it still start to look like a T table. A T graph will look a bit like a Z graph. Okay, everybody comfortable? If we move on to page 24, can you see we've dealt with quite a few distributions so far? This entire learning module 4 deals principally with the various types of distributions. Page 24, we talk about properties of the chi-square distribution and the F. Okay, a chi-square distribution, okay, is positively skewed. Can you see over here, guys? It only works on the right hand side. So there's a 0 there, and it only works to the right. It's truncated at 0. Okay, it cannot be defined for negative values. Okay, same story. The graph becomes more and more symmetrical as we increase the degrees of freedom. In other words, the sample size. Critical values for this particular distribution, where would you find these? This is a third table. Guys, we so far dealt with the Z table. Everybody comfortable? Okay. A T table. Now a chi-square table. Okay. We move on to the F distribution. We're not going to spend too much time on the F distribution. Okay. Unlike the T and the Z graphs, similar to a chi-square graph, the F is also positively skewed, truncated at 0. In other words, it doesn't become negative. Okay, there we go. Like the family of T graphs and my chi, the shape of the graph will change and it will become more and more symmetrical as we increase the sample size or the degrees of freedom. Everybody comfortable? Oops. Okay, there we go. And there we go. You can see the graph looks very much like a chi-square graph, doesn't it? Okay, the one area in which F tests will differ from chi is that the rejection region is always in the right hand, not in the left hand tail. This does present a few difficulties. Okay, if we are conducting a one-sided test, the full value will go now into the right hand tail as opposed to being able to work with two tails. If it is a two-sided test, we would take our what we call the level of significance and divide that by 2. We'll see, by the way, don't stress now, guys. We'll see more about level of significance and things like that in learning modules 5 and 6. Unfortunately for you, the critical values for this particular distribution are found in the F table. Now we've got 4 tables so far: Z, T, chi-square, and the F tables as well. We're going to show you those in the appendix in learning module number 7. That then brings us to a conclusion of learning module 4, common probability distributions. In and of itself, well, not so much to examine over here, other than it's massively important as an introduction to learning module 5, which will be sampling and estimation, and then of course learning module 6, which then will be hypothesis testing. So please spend a bit of time over here. Make sure you are familiar with the particular content. Once you are done, as you know me by now, guys, I always page back to the very beginning again, the very best place to start. And please, guys, always go over those learning outcome statements again. Okay. And just make sure that we talk about these, okay, explain how to standardize a random variable. Now, if that looks familiar to you, say, yes, I can do that. I know how to do the Z thing. What was that, guys, again? Oh, that was X minus the mu over the standard deviation. That's how you standardize a random variable. Then I go and look on the Z table, then I get a number. Oh, okay, I can do all that. You're in a very good space. If not, and these learning outcome statements are looking a bit foreign to you, probably best to go and do a bit of revision then on those. Coming up, learning module number 5.